Consider the following game. You have a fair coin, so the odds of having a heads or tails is equal, both 0.5. So you flip the coin until you get an equal number of heads and tails. So what you need to do is think of how many flips you would need to maximize the probability of having an equal number of heads and tails. So what do you think the answer will be? You would probably think it's a high number, like, I don't know, 1,000, or the probability gets larger as it approaches infinity. However, that is not the case. The answer is in fact 2. So 2 flips is the number that will get you the highest probability of getting an equal number of heads and tails, and the proof is as follows. So there's a formula you should be familiar with, and that formula is the binomial probability distribution. So if we assume that the number of heads is distributed binomially, with n being the number of trials and p being the probability of success, your formula is probability of h equals k, which is the number of successes, is n choose k multiplied by p to the k multiplied by 1 minus p to the n minus k. So in our case, p is a half and k is n over 2, because we want half of the trials to be heads. So the probability of h heads equals to n over 2 is equal to n, number of trials, choose n over 2, multiplied by p, the probability, to the power of k, the amount of trials, which in our case is 0.5, because that's a probability, and that's k is n over 2, so it's the n over 2, multiplied by 0.5 to the n over 2. We simplify that, we get n choose n over 2 multiplied by 0.5 to the n, which is also equal to n choose 2, so n choose a half, n over 2, divided by 2 to the power of n. So we can rewrite it as this. So this is the formula we get. Now we can plot the function we derived in Desmos and see what it looks like. As you can see in this Desmos plot, the probability of getting equal number of heads and tails is a maximum at 2 flips, and then it decreases as the value of the number of flips increases. So, you might still not believe me. However, I can show you proof that this is the case using a simulation I coded in Python. So, let's have a look. So, in this graph, you have the absolute difference between heads and tails on the y-axis and the number of flips on the x-axis. The red curve shows the heads and the value of the absolute difference between the heads and tails for a given number of flips, and that is the mean from the 1,000 simulations. The red boundary shows the plus minus 1 standard deviation, and all the blue lines in the background are the curves that the mean of were taken. So this shows you that for the number of flips being 2, the absolute difference between the heads and tails is 0. So the largest probability for, if you want the difference to be 0, is actually 2, and then you can see that as the number of flips gets larger, the absolute difference between the heads and tails also gets larger, which corresponds to what the previous curve was showing and what the formula was demonstrating. So I hope you enjoyed this video, and please like and subscribe so you can see the next videos I'm going to upload soon.